Bismillahirrahmanirrahim. Assalamu alaikum. Dear students, I am Sahib Noor and welcome to a new lecture of Electromagnetic Field Theory. This is our lecture number 8 and we will study topics from chapter number 2. The title name of the chapter is Vector Analysis. Our main topic of this lecture is to discuss the curl of a gradient of a scalar field, and also we will discuss the divergence of a curl of a vector field. These two are called the null identities. And then we will discuss a theorem which is about the divergence and the curl of a vector field, and we will combine them, the divergence and the curl of a vector field, in a single equation, and then we will present few examples to understand our lecture. So let's start our lecture, and we will discuss the first null identity, in which we have to prove that curl of a gradient of a scalar field is always equal to 0. Mathematically it can be written as the del cross del into v is always equal to 0. This part of the equation represents the gradient of a scalar function, which will be a vector quantity, and then we will take the curl of this result, and our answer will always be equal to 0. So we can say that the curl of a gradient of a scalar function is always equal to 0. And as f is a scalar function and it can be depend upon the coordinates of position, so we take the coordinate system as a Cartesian coordinates, and the gradient of v in Cartesian coordinate can be written as grad v is equal to del v, and the component of the gradient of v in Cartesian coordinate is given as ax del over del x plus ay del v or del y plus az del v by del z. So these are the three components of the gradient of a scalar function v, which is a vector quantity, because we have the base unit vectors of the Cartesian coordinates at the right hand side of the equation. Now we are going to take the curl of the above equation, and in the Cartesian coordinate the curl of any vector can be written as, in the determined form, the first row is for the base unit vector, which are ax, ay and az, and in the second row we have to write the operator, which are del over del x, del over del y and del over del z, and then we have to write the component of the gradient of a scalar function v, which are del v by del x, del v by del y and del v by del z. So when we expand this matrix with the help of with the first row, so the coefficient of ax will be like ax into del or del y into del v by del z minus del or del z into del v by del y, and we have to write those elements which doesn't lie in the first row and first column. So we are left with the del or del y into del v by del z minus del or del z into del v by del y. So if you look at this part of the equation, so we have the derivative which have the reverse order. We have two terms, and in both terms the derivative are the same, which are with respect to del and with respect to y and z, and if we reverse the order of any term in this coefficient, so we will obtain exactly the second term, which is cancel with one another. So the coefficient of ax is thus equal to 0. So the remaining coefficients of ay and az is always equal to 0. So the right hand side of the equation is equal to 0, and hence the curl of a gradient of any scalar function is always equal to 0. And conversely, we can also say that if a vector field is curl free, that is the curl of any vector, we took E as an example. So if the curl of E is equal to 0, we will call it a curl free field. Then E can be written as, E is a vector, then E can be written as a gradient of a negative gradient of some scalar potential. So we summarize that if a vector field is curl free, that is curl of E is equal to 0, then we can write E as a negative gradient of some scalar potential. Here V is a scalar potential which can be a function of coordinates x, y, z, or r phi z, or r theta phi. So any curl free vector can be written as a negative gradient of some scalar potential, and such a curl free, which is an irrotational field, is also known as a conservative field. And in the property of the conservative field is that when work has been done by a force, then that work will be independent on the path chosen. In this slide we will discuss the second null identity, which is related with the divergence of a curl of a vector. And the divergence of a curl of a vector field is always equal to 0. So we have to show that del dot del cross A, where A is a vector, is always equal to 0. So to prove this identity, we take the volume integral on the left hand side, and then using the divergence theorem, and we will convert them into the surface integral. So first we took the volume integral, and then applying the divergence theorem, so we will have the volume integral of a curl, the volume integral of the divergence of a curl of a vector field A can be written as the surface integral of a curl of that vector through the closed surface. So as we told that we took first the volume integral, and then we apply the divergence theorem and convert the volume integral into the surface integral, and we call it equation number 1. So we take the right hand side of this equation and split this closed surface into two open surface. So we split this closed surface S into two open surface S1 and S2 connected by a common boundary which has been drawn twice as C1 and C2. C1 and C2 are representing the contour, which are the open surface of a single closed surface. So we split the closed surface into two open surface, which are S1 and S2, and it can be easily shown from the figure. We have a single closed surface, and we split the surface of this closed body into two open surface by drawing two contour C1 and C2. So the closed surface which are splitted into two open surface, and this equation can be converted to the line integral by applying the Stokes theorem. So the right hand side of the above equation can be written in terms of the line integral by applying the Stokes theorem as contour C1 and del dot A, which represent the line integral over the closed path C1, and we can also apply the stroke theorem of the second part of this equation and will obtain a line integral A dot dl or a closed path C2, as C1 and C2 are two representing two closed loop. So these two line integrals on the right hand side of the equation traverse the same path. Traverse mean cover the same path in opposite direction, so there will be a positive and a negative term. So the sum of these two line integral will be equal to 0, and thus the volume integral del dot del cross A in equation 1 is become 0. And we can also say that the a vector which is a divergenceless or a solenoidal, then it can be expressed as a curl of another vector, as divergence of B is always equal to 0. So this must be a solenoidal. So if the divergence of B is equal to 0, then B must be a solenoidal, and we can write B as a curl of another vector. So B is equal to curl of A. Here A is known as magnetic vector potential. Now, after discussing the divergence and curl of a vector function, we can write different properties of a vector field, and this will be based for the Helmholtz theorem. So if a vector field is solenoidal and irrotational, then mathematically it can be written as del dot f is equal to 0, because it is solenoidal. Then the divergence of the function will be 0, and if the f is a irrotational function field, then the curl of the field is also equal to 0, because it is irrotational. So if it is irrotational, then the curl will be equal to 0. And the example of such a field which is solenoidal and irrotational can be taken as static electric field, which is for the static charge. And if a vector field is solenoidal but not irrotational, then mathematically it can be written as del dot f is equal to 0, and the curl of f is non-zero. Because it is solenoidal, then the divergence part will be 0, and it is not irrotational, so the curl will be non-zero. And the example of such a field is the static magnetic field, steady magnetic field, or the magnetic field due to a steady current in a conductor. And if a vector field is irrotational but not solenoidal, then mathematically it can be written as curl of f is equal to 0, because it is irrotational, so the curl will be 0, and divergence of f will be not is equal to 0, because it is not solenoidal. Then the example of such a field is a static field in a charge region. And if a function is neither solenoidal nor irrotational, then mathematically it can be represented as divergence of f not equal to 0, and the curl of f is also a non-zero. So the example of such a field which is neither solenoidal nor irrotational, the example is the electric field in a charge medium with time varying magnetic field, or when the charge oscillate on a conductor in up and down, or into and fro motion. So this will establish a time varying magnetic field. Now let's summarize them and write the definition of the Helmholtz theorem. So the most general vector field has both non-zero divergence and non-zero curl. So we can define Helmholtz theorem. A vector field is determined to within an additive constant if both its divergence and curl are specified anywhere. So we can determine a vector field from some additive constants if the divergence and the curl of the function is specified, is determined everywhere, and thus we can decompose a general vector f into a rotational part which is represented by fi and a solenoidal part which is represented by fs. Let f is a general vector field, so we can write f is equal to fi plus fs. We split the general vector field into two parts, fi which represent the irrotational part of f and fs represent the solenoidal part of a vector field f. And for fi, if the function is irrotational, then the curl part of f will be equal to 0. So curl of fi is equal to 0 and the divergence will be a non-zero. So divergence del dot fi will give us a value, and we represent this value as a g, where g is a scalar quantity, small g is a scalar quantity. And if for fs, which is a solenoidal part, the divergence of fs will be equal to 0 and the curl will be a non-zero, and we take g as the answer of the curl of the solenoidal part. Here g is a vector quantity, and where the small g and capital G are known to us, or it can be known everywhere. So if we take the divergence of a vector f, the general vector, the answer will be g, and if we take curl of vector f, the answer will be capital G. Therefore f must be obtained by integrating the g, small g and the capital G, which will lead us to a constant of integration. Now in this slide we will present an example in which we will determine the constant of an irrotational function. The function is given is ax into 3y minus c1z plus ay c2x minus 2z minus az into c3y plus z. So the given function f is in the Cartesian coordinate, and as the function is irrotational, so its curl must be equal to 0, and we can obtain the curl of this function by using the formula of the curl in the Cartesian coordinate. So we will use the determinant method, and in first form of the determinant we will write the element of the base unit vectors, which are ax, ay and az. In second row we will write the differential operator, which are del over del x, del over del y and del over del z. And in third row we will write the component of f, which are 3. So 3y minus c1 z will be right at the first part of first place of third row, and then the second component and third component. After calculating the determinant, we obtain this expression ax into minus c3 plus 2 minus ay c1 minus az into c2 minus 3 equal to 0, is the curl of irrotational function is always equal to 0. Now we will compare the coefficient of ax, ay and az on both sides. So the coefficient of ax on the left hand side is minus 3 plus 2, and the coefficient of ax on the right hand side is 0. So we can obtain c3 is equal to 2, and c1 will be equal to 0 and C2 will be equal to 3. So C1 is equal to 0, C2 is equal to 3, and C3 equal to 2. So these are the constant which appear in the irrotational function. By inserting them, we can write the function as f is equal to ax 3y plus ay 3x minus 2 into z minus az 2y plus z. So this is an irrotational function, and now this is a constant less, means that we insert the constant terms. So now if we take the curl of this vector, the curl of this vector will be equal to 0. Now once we have an irrotational function, that is the curl of f is equal to 0, then we can obtain a scalar potential in which we can write f as a negative gradient of that scalar potential. So our function which is obtained in previous slide, f is equal to ax into 3y plus ay into 3x minus 2z minus az 2y plus z. And we know that if the field is irrotational, then the curl of f is equal to 0, and we can write f as a negative gradient of some scalar potential. In the Cartesian coordinate is given as ax del over del v or del x, ay minus ay del v by del y minus az del v by del z. So these are the three components of the gradient of a scalar potential v, and f has also three components. So we write f on the left hand side of the equation. These are three terms of the vector f, and the right hand side we are three components of the gradient of a scalar potential v. And now we will compare the coefficient of ax on both sides. So the coefficient of ax on the left hand side is 3y, while the coefficient of ax on the right hand side is minus del v by del x. And similarly we can also compare the coefficient of ay and az. So del v by del y is equal to minus 3x plus 2z, and del v by del z is equal to 2y plus z. Now we can obtain v from here by integrating this equation with respect to x, and we will obtain vx is equal to minus 3y plus minus 3yx plus a constant which is a function of y and z. From here we can integrate this expression with respect to y, so we can obtain minus 3y minus 3xy plus 2yz, and a function which is function of x and z. And finally we can also integrate the last term with respect to z, and we will obtain vz is equal to 2y z plus z square divided by 2, and some constant which is function of x and y. So our scalar potential must be like minus 3yx or minus 3xy plus 2yz plus z square divided by 2. So let's summarize our lecture number 8. What we have studied in this lecture, we have discussed two null identities in which we have obtained that the curl of a gradient of a scalar function is always equal to 0, and in second identity we show that the divergence of a curl of a vector field is always equal to 0. And then we have discussed a theorem in which we write the divergence and curl of a same function in a single equation. And finally we discussed few examples which are related with irrotational function, and if a function is irrotational, then the curl of the function will be always equal to 0. and the function can be written as a negative gradient of some scalar potential. In next lecture we will start our new chapter, which is related about electric charge and electrostatic field. So our next lecture will be to study the property of electric charge and electrostatic field. And if you feel any difficulties related to this lecture, you can contact me at my email. Thanks and Allah Hafiz.